Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 13, Periodic Motion, Video 6. Today's topic is the simple pendulum. The objectives are: know the definition of a simple pendulum, understand for small angular displacement theta, the oscillations of simple pendulum are simple harmonic, be able to analyze the motion of a simple pendulum. A simple pendulum is an idealized model consisting of a point mass suspended by a massless unstretchable string. So when the point mass is put to one side of its straight down equilibrium position and released, it oscillates about the equilibrium position. So here is a real pendulum. This is idealized pendulum. This string is unstretchable, and all the mass is concentrated at the end, which we call it a bob. So that's a simple pendulum. Here is a real pendulum. The motion of simple pendulum is a simple harmonic. Let's see how we got to that conclusion. Here is an idealized simple pendulum. So string is assumed to be massless and unstretchable. The bob is modeled as a point mass. So on the bob, there are two forces. One is gravity, one is tension. So since the bob is moving in an arc, that's a two-dimensional motion. Whenever it's moving in two dimensions, there are two accelerations. One is the radial acceleration, the other one is tangential acceleration. Radial acceleration is the same as centripetal acceleration, which is t minus mg cosine theta. That's a centripetal force divided by mass that gives you centripetal acceleration. The other acceleration is tangential acceleration. That's a tangential part of the gravity divided by mass. And that tangential force is the restoring force. The restoring force is tangential component of the gravity. F theta equals negative mg sine theta. Negative over here means F theta and theta are always opposite in direction. So when theta is to the right, F theta is to the left. If theta is small, sine theta equals to theta, approximately equals to theta. So F theta equals a negative mg times theta. Theta is in radian. Radian is the arc length divided by the radius. Arc length is x, radius is L. We substitute this theta into F theta equals a negative mg theta. So we get negative mg over L times x. So this is in the same form as a simple pendulum, as a simple harmonic motion, Fx equals negative kx. So for the small theta, the pendulum motion is approximately simple harmonic. So pendulum is only simple harmonic when theta is small. So in this case, what is k? K equals mg over L. So we can plug in this in, omega equals to k over m for simple harmonic motion. So that equals to square root of g over L. T equals to 2 pi divided by omega. So t equals to 2 pi square root of L over g. That is the t only equals to this for simple harmonic motion when theta is small. Otherwise, t would be changing if theta is too big. Let's look at the graphs of t versus L and t versus the square root of L. Here is the equation, t equals to 2 pi L over g. So t versus L is square root of relation, direct square root. That is a curve. Up looks like this. But t versus square root of L, that's a direct relationship. We can rewrite this relationship as t equals to 2 pi divided by square root of g times square root of L. So t and L, square root of L, are directly related. So the line is a straight line. The slope is 2 pi divided by square root of g. From this slope, we can find value of g. So a lot of times on a test, you may given a set of data, t versus L. From there, you have to find g. How do you do that? Using graphs. So you have to plug the t versus square root of L graph. From there, you'll find the slope. Then from the slope, you'll find the g. Let's take a look at this example. Find the period and frequency of a simple pendulum of 1 meter long at a location where g equals 9.8 meters per second squared. This is kind of like straightforward. G equals 2 pi L over G. You know L is 1 meter. You know G is 9.8. So you plug it in. T is about 2 seconds. The frequency is 1 over T. That gives you 0.5 hertz. Test your understanding. So when a body oscillating on a horizontal spring passes through its equilibrium position, its acceleration is 0. When a bob of an oscillating simple pendulum passes through its equilibrium position, is its acceleration 0? So let's take a look. The answer is no. For a pendulum, when it's at equilibrium position, which is on the bottom, it has centripetal acceleration because velocity is not 0. Hence, there is a net force, centripetal force, acting on the bob, causing a change in direction of the motion. So the acceleration is not 0. That's it for today. Thanks for watching.